right. I'll change the slide.
So is everyone finished? Okay. So here you can help us to collect the feedback. Thanks for leaving your suggestions or comments. I will carefully go through every sentence you wrote during spring break, and when you return from spring break, I will discuss our mind results and say what kind of way to say how we further improve and better help you in this class during the remaining of the semester. Okay. So let us continue with support machines. In the last lecture, we introduced the learning principle of support machines. The principle is to maximize the margin. Right? So intuitively, the larger the margin a classifier has, the farther away the classification boundary is from the high density regions, so we have a low risk to make more mistakes, right? And then we justify our intuition, because this is just some qualitative analysis, just intuition, right? With this computational learning theory, how can we justify it? We use the generalization error bound. So it turns out, that if you can focus on a subset of linear classifiers with some designated level of margin, then the VC dimension of that subset of linear classifiers will vary, right? So the larger the margin, the smaller the VC dimension of that subset of linear classifiers. That is what we get, right? In the last lecture. This is called data dependent VC dimension. So the key idea here is that when we design a learning algorithm to search for some linear classifiers, we're not gonna search entire space. If you search entire space, the VC dimension for the whole linear classifier hypothesis space is fixed. You cannot improve you cannot improve your generalization error bound, right? VC dimension for the linear classifiers in d-dimensional input space is simply d+1, right? So whatever learning algorithm, if you just search entire space, you end up with the same bound. So then the trick is that why not we just ignore most of the linear classifiers? We just focus on searching over a small subset of linear classifiers. And because now we reduce the range of linear classifiers for search, the VC dimension is reduced as well. According to our generalization error bound, when you have a smaller VC dimension, you have a simpler model, and you end up with a tighter generalization error bound. So you're more likely to have a smaller generalization error. That's the idea. And that's how we justify why learning a linear classifier with large margin will be better. And also how we motivate the principle of learning linear classifiers. That is to maximize the margin of linear classifiers, right? So what if we just design our algorithm to search for a subset of linear classifier with the largest margin. So now you can imagine this particular subset of linear classifiers, which might probably only contain one linear classifier, has the smallest with dimension, right? Then you might have the tightest generalization ever one. So that's the key idea. So it's very brief summarization, and hope can refresh our memory, right? And then we, given this maximizing margin learning principle, right? We talk about how to turn this principle into a direct objective function, right? Because when we implement a learning algorithm, we need to develop an algorithm, right? We need to fulfill this principle. Then what kind of objective function did we use first? What is the outright translation from maximal margin principle to some optimization problem?
Are you talking about what we were using?
What?
Are you talking about what we were using?
Yeah.
Read?
No, we haven't moved to the reading step. We just talk about like what kind of objective function you should formulate that reflect the maximal margin learning principle.
We pull the substitution, forcing the values of the function into one.
Oh, that's the next step. We just look at the original step, the preliminary step. We just directly translate this learning principle, right? How do we maximize the margin? So first we look for the definition of margin, mathematical definition of margin. Margin is defined as the distance of the closest point of data from the hyperplane, right? So when we write down the margin in mathematical formulas, we just write it as minimization over all the distances between the points and hyperplanes, right? So it's maximization over all the training examples. So this is the distance between this particular example xi and the hyperplane. And now our objective becomes maximizing this margin, right? So we can substitute this minimization procedure, minimization formula for gamma here. So end up with our first optimization problem, which is a max-min problem. Right? It's max-min problem. So this is some outright translation. And if we want to train our SVM model, we can just solve this max-min optimization problem to find out the best with vector and the box parameter. Sorry, I missed a B here. I missed the box parameter here. But there's a severe problem here. So max-min optimization is never an easy optimization problem because you are not looking for some local minimum nor some local maximum. You are looking for a kind of saddle point, meaning that they have the gradient being zero, but they're not local minimum, they're not maximum, local maximum. So typically, solving such kind of problem is hard. So then, naturally, we want to further simplify this objective function, right? Simplify this optimization problem. The trick here is we realize that because we're doing linear classification, right? So the prediction only depends on the sign of the classification function value. So no matter how you scale up your model parameters and scale down your model parameters, as long as you don't change the sign, they're totally equivalent, right? So then naturally, think about why now we like intentionally set the absolute score, that is the function margin here, of the closest point to B1. Then our margin becomes 1 over the norm of the So basically, we set the minimum value of these numerators among all the training examples is 1. Then our margin is just 1 over normal of the vector. There's no numerator. And then our optimization becomes to maximizing this inverse norm of big vector. So that's the idea. Because you're free to skew your big vector and bias parameter. As long as you don't change the sign, they are totally equivalent. So we can put these extra constraints. And based on this idea, we reformulate our learning problem as follows. Right? So first, we maximize the margin, which is inverse norm of the W, right, the weight vector, and it is totally equivalent to minimize the square norm of W, which is the W transpose W, right? We can multiply with a constant 1 over 2. It's just for convenience, no other meanings. And then to reflect our intentional restriction that the smallest function margin to be 1, we put a set of constraints here. We will require that for any training example, say xi by I, we must have the function margin less than 1.
If we determine that none of them have margins that are less than 1, trace that down to like 0.5, or would that explode the rest of the...
So if you train your model, you actually can like restrict this one to be like 0.5 or 0.2 or 1,000, doesn't matter. The reason is when you set up this region, when you set up these constraints, you designate that your smallest function margin is simply the value set. Why? Because suppose I set 1, right? And now I set it to 10. I just multiply the weight vector and bias parameter by 10. I satisfy the new value I got. Right? So 1, you can replace 1 by any like possible constant 1. But here just for convenience. Any questions so far? This is very important for you to understand the formulation of small vector machines. This is a classical formulation, and all the extensions are based on this. Because we recognize like the flexibility to skew the model parameters, right? So I can intentionally set the functional margin. Remember the definition of function margin, right? This definition of function margin is just the production between the true label and the classification function value, right? I can intentionally set the functional margin to be arbitrary value I want, but it must be possible. But here, 1 is simply for convenience. Any question so far? Okay. And here, this set of constraints, as we just emphasized, right? Just to reflect our intentional setting of the skew of the function margins. That's it. And this formulation is called hard SVM. Why? Because we assume the data is linearly separate. Then at the end of the last lecture, we asked, what if the data is not linearly separate? What will happen if we are still trying to solve this hard SVM? An idea? What if the data is not linearly separable? I just want to solve this hard SVM optimization problem. Then what model parameters will we get?
So there's no physical solutions.
Yes, right? There's no physical solutions. I've actually discussed in the last few minutes on Monday, right? So why? Because if the data is not linearly separable, that means there at least exists one data point such that this function margin is less than 0, right? If it is all like bigger than 0, then you can correctly predict all the examples. Remember, we discussed this point, right? So whenever you correctly predict one example, we have this function margin to be non-negative, right? So now if the data is not linearly separable, that means for arbitrary model parameters that will be, there always exists at least one training example such that the function margin is less than 0. That means those constraints, those set of constraints for all the training examples will never be totally satisfied. Right? Basically says there is no physical region, or the physical region is empty. So what's the physical region? Does anyone forgot?
Feasible region?
Yeah, feasible region. Is anyone unclear about the definition of feasible region?
You're talking about like the region formed by the constraints?
Yes, exactly. Right. So this is a term from optimization, right? So basically, if I want to solve a constraint optimization problem, I can put a constraint. I can put a set of constraints, right? Those set of constraints actually form a range, right? You can only search your minimum of the cost function inside this range, right? This range is called feasible region. So now you can say, okay, our feasible region is determined by this set of linear inequalities, right? But if our data is not linearly separable, this range is empty. So you cannot search. That means you do not have a chance to try like even one lead vector and loss parameter. Okay. So that's the problem of hard SVM, right? So actually, in practice, we can never guarantee that your data is linearly separable. Right? What if it is not linearly separable, right? And you run it, and you get a response that we don't have any with vector and bias parameter for you. We will be very frustrated, right? I hope I solve this problem. How can I solve this problem? Any idea?
Try throwing out the outliers.
Yeah, exactly. It's very intuitive, right? So now that there are some there are data points which make the whole data set not linearly separable, so can we automatically identify those data points and throw them out? And for the remaining points, they're still linearly separable. Then I try to maximize the margin for linear classifier that separate the remaining data points. So that's the basic idea. So, so now let us look at definition. It's called soft SVM. So the key idea is that we allow some examples to break into the margin. So basically, assume here are our training examples, right? So we have negative examples here, positive examples here. So it looks like the data is mostly linearly separable, except that we have these 2 points, right? And because of these 2 points, negative and positive examples, the outliers, as we just mentioned, we cannot find any hyperplanes to well separate all the examples. These 2 points, right? So then why not we just ignore these 2 samples? We just throw them out. Or in other words, we search for the hyperplanes that always separate the remaining points. And we allow these 2 outliers to break into the margin. So because we only remove 2 outliers, right? So we do not largely reduced number of training examples, and our new separator still has a large margin. So we can expect that it still end up with good generalization performance. That's the idea. So basically, when we compute the margin, right, we're not trying to enforce every example to be correctly classified. Instead, we ignore some examples that could make the margin very small, or even make the data inseparable, and just look for the margins. Look for the margins for the remaining data set, and for the remaining data points, the larger the margin, the better your generalization performance. So this is the idea. So now let us look at how can we turn this idea into a optimization problem, right? A new optimization problem. This is a hard SVM. Right? So now to allow some examples to break into the margin, we introduce one slack variable, KCI, for each example, for each training example. Right? And then we modify this constraint a little bit to be like function margin must be no less than 1 minus this slack variable KCI. At the same time, I want this slack variable to be non-negative. So now, if KCI is bigger than 0, what does it mean? What if KCI is bigger than 0?
It breaks into the margin.
Yes, exactly right. We want to add flexibility that some examples can break into the margin. Right? So of course, if KCI is bigger than 0, then we know this hard constraint won't be satisfied. Only this soft constraint is satisfied, right? And that means, okay, this particular example xi may break into the margin. So when we trying to learn linear classifiers that maximize margin or maximize margin for the remaining data sets, remaining data points. And what if the CI is simply 0? Yeah, that means it still sticks to the hard constraint, meaning that this data point is outside the margin or stays right on the margin, right? So now comes out our soft SVM formulation. So first, we introduce a slack variable CI for each training example xi, and label by I. And we modify the constraint to be like 2 constraints. The first constraint is that the slack variable is non-negative, and the second constraint is that function margin is less than 1 minus CI. So the question here is that why we must make CI to be non-negative. What if CI is negative? An idea?
Yeah, it's the same issue as before. You would just be adding 1 or 2.
Yes, exactly right. If CI is negative, that means you put even severe constraint, right? Even more severe constraint. You want your function margin is bigger than 1. It's bigger than, say, 1 plus 0.5, right? So you want to push your examples to be even farther away from the margin. But here, the motivation for us to incorporate the CI is that we want to allow some examples to be closer to the classification boundary, such that it can even breaks into the margin. So here, that's why we make the constraint that KCI must be non-negative. And another thing that we change is that in the cost function, in addition to this half of the square null, we add 1 extra component, which is the summation of those slack variables. And and multiplying with a hyperparameter C. So why would I like to append this extra summation? Why not we just remove this? We just maximize margin, right? And use this set of constraints.
You want that character, I don't remember what that Greek character is called. You want that one to be as small as
Kasi,
possible.
yeah, kasi.
What?
It's called kasi.
Sorry?
It's called kasai. Kasi.
Side.
Yeah, you can call it kasi or kasai or
You
whatever.
want that value to be as small as possible to maintain the large margin still, right? So
But you can think about this problem, right? Why not I just allow most of the examples to break into margin? And I can even get even larger margin, right? So take this for example, right? So why not I ignore like most of the negative examples and most of the positive examples? I just choose the one positive, one negative, which are farthest to each other. I just found a margin to separate these two examples. I can imagine that I can put the margin to be here and here, right? It's much larger. Why not do this? What's the problem here? What's the problem?
it doesn't matter if you have a big margin if you're ignoring a large percentage of the examples.
Yes. So the idea I just mentioned, I just proposed, right? Indeed can improve your margin, enlarge your margin. That means your data-dependent basic dimension will be largely reduced. That's true. But the problem is that, let's just remember, right? So the generalization error is upper bounded by two terms. One term is the training error. The other term is determining the basic dimension, right? So we just like ignore most of the training examples. To break into margin, that means you misclassify most of the training examples. You have a very large training error, right? So of course, at the same time, you like significantly reduce the other term, which is determining the basic dimension. But we'll take them together. You might still end up with a large error bound, right? So this is actually a trade-off, right? So we want our margin to be as large as possible, but we do not want to misclassify most training examples. Then we incorporate this term. We want to allow as few examples as possible to break into the margin. That means we want to minimize the training error at the same time, right? So this term just penalize the number of examples who break into the margin. The ideal case is that this term is simply 0. That means each KCI is simply 0, and means each training example is outside the margin or on the margin. And now, if there are some examples who break into the margin, we put some penalty here. That means we still maintain, or we still pursue most of the training examples to be correctly classified. At the same time, if the corresponding margin is larger, it will be better. So any question at this point? It's a very important point. Everyone is comfortable, right? Okay. Right. So the major difference between hard SVM and soft SVM, and let me emphasize the meaning of this whole formulation, the soft SVM formulation again. Right? So in the cost function, we have two components. The first component is half of the square norm, which is half multiplying with inner product between W and W. And then there's another component, which is the summation of all the slack variables. So the function or the meaning of this summation is to minimize total slack variables so that we allow as few examples as possible to violate the margin. Doing so can help us to prevent large training error, right? Because the generalization error is determined by both the training error and some term determined by the VC dimension. So if you just end up with very large VC dimension but very large training error as well, then when you combine together, you still end up with like suboptimal like generalization error. And to choose the balance between the two terms, we assign a hyperparameter C. So it indicates a trade-off between the two terms. So someone may ask, how do we set up this C, right? Unfortunately, you cannot learn C from the data. That's why it's called hyperparameter. You need to manually tune them from data. And later we'll discuss a general framework to tune all kinds of hyperparameters, including this C here and number of epochs in your perception, or learning rate in your stochastic gradient descent, and so on. It's called cross-validation. So usually this hyperparameter C is chosen by cross-validation. You partition the data into multiple subsets and use one set for test, the other for training, and you do this alternatively, take the average, you get the estimation of the generalization performance when you use a particular setting of hyperparameters. It's the basic idea. So now, let us look at how we solve this problem. Right? We have formulated a new optimization problem. It's called soft SVM, such that we can deal with all kinds of data. Right? We do not enforce that you must have you must be linear separable. Even if your data is not linearly separable, that works well, right? And then the remaining problem is how to solve it. So it turns out that this optimization problem is still like complicated. Why? Because we put many constraints. So although the objective function, the cost function is relatively easy, but we have many linear constraints. Right? For each example, we have two constraints. One constraint is for the function margin, the other constraint is for the select variables. And now let us think about can we further simplify this optimization problem? Is it possible for us to just eliminate this slack variable? So first, we'll look at each slack variable, right? So the first constraint, you can simply move the CI to the left-hand side, move function margin to the right-hand side. You see that this slack variable is no less than 1 minus function margin, right? And for the second constraint, simply that the CI must be non-negative. So we combine them together. You know that the CI must be no less than the maximum value of 0 and 1 minus function margin, right? So now, let us look back to the cost function. So remember, the cost function is to minimize this. The cost function is cost function, and we want to minimize this cost function. So that means if we fix W, and we want the CI to be as small as possible. So the question is that, what is the minimum value the CI can choose? Any idea? Any guess?
One of those two, either 0 or 1 minus the function.
Yeah, exactly, right? So no, okay, this is a minimization problem, right? You want to minimize this cost function with respect to our model parameters. So suppose our W, the weight vector and bias parameter is fixed, and then what is the minimum value of KCI I can choose? We can look for the constraints, right? From constraint, we know that KCI is must be no less than 1 minus function margin and 0, right? So the minimum value we can choose must be the maximum of 0 or 1 minus this function margin. So we can simply replace KCI, the cost function, by the maximum value of 0 and 1 minus the function margin. Then we can totally discard KCI, select variables. We end up with this more succinct and easier cost function. Right? So now, KCI is directly replaced by the minimum value we can choose. And this form.
I understand why we have the max 0 and 1 minus that, but I'm wondering what would happen if we didn't have the 0 in there. Would we let it be as small as it was?
You mean you don't have 0 here?
Yeah, what would happen to our numerization problem?
Well, that's a good question, because we previously we just asked, right? What if we allow KCI to be negative? What will happen? Right? So from the meaning of our classifiers, KCI is free, right? It's negative. Then we want to constrain the function margin to be bigger than 1. Say KCI can take like 0.5, then your function margin is constrained to be bigger than 1.5. So it's even harder. It is even more aggressive than the hard SVM. The hard SVM only require you like your function margin is no less than 1. But now I want you to no less than 1.5. You must be even further away from the classification boundary. But hard SVM still also has a severe problem. When the data is not linearly separable, you just restrict to be no less than 1, you can not have any results. Now you restrict to be bigger than 0.5. It's even more impossible to get any feasible solutions. So that's why we put this constraint here. And now we just look at this formulation. We forget. We can just discard the original meaning and we turn them into this equivalent optimization problem. That's the idea. Any questions?
Yeah, in general, like, what is the range of that C term?
C must be no less than 0. But there's no like definite range for that.
Yeah.
And it's interesting that in this whole machines, it's not like in other models. So C is not. I kind of have a feeling that you would think like C is between 0 and 1, but it's not true. C can be 10 or even 100. So what you do in practice is just try a set of C values. You can set C to be like abruptly large, like even very absurd, like 1 million. It is possible, and you figure out a way to adjust the C every time you do the cross validation. Any other question? Okay, so this most succinct formulation of supply SVM can give us some more interpretation. So let us look at it. So now we don't have any constraints. This is an unconstrained optimization problem. And we have one component in the first, the first component is to maximize margin. And the second component is replaced by the summation of this max function, x of 0 and 1 minus function margin. So this actually activates the penalty for the prediction. Let us do analysis. So let us look at what kind of values can this max function take. So actually there are 3 cases. So first, if the example xi y is correctly classified and xi is outside margin, what is value? What is the value of this max function? So first, we know A is correctly classified, right? So we know this function margin must be non-negative, right? And second, we said, okay, this example is even farther away from the classification boundary such that it's outside margin. What does it mean?
There's no penalty?
Yeah, of course. This is a consequence, right? And why there's no penalty?
If the margin is greater than 1, then that term would be negative. So it's 0 is the maximum.
Yeah. So remember that we restrict that the margin, the smallest function margin is just 1. Right? So now if it's outside margin, that just means the function margin is bigger than 1. Then 1 minus some value bigger than 1 is just negative. If you take max of 0 and it's negative value, it now will be 0, right? That's why we say, okay, there is 0 penalty, right? We are happy. We are satisfied with this example because we,
why, so, what if we reward, like, instead of, setting it to 0, like, if it was super outside the margin, would we want to reward that?
Well, that's a good question. You can like come out your own objective function to prove this actually work. But here, for this soft SVM formulation, there is no reward. As long you can say, okay, my reward has reached the maximum because I have 0 penalty. That's it. But you can definitely like modify this penalty function to introduce some actual reward. Yeah, it's doable. Definitely doable. So this is the first case, right? So the second case that, okay, the example is incorrectly classified. And what is the penalty? Or what is the function? What is value of this function? So if we misclassify the example, so what is the function margin? I heard that. It must be negative, right? If you misclassify the production of the ground truth and your classification function value must be negative, 1 minus inactive value is even bigger than 1, right? And the max text here is simply this 1 minus function margin, right? So you got penalty which is bigger than 1. Remember, although this is a minus sign here, and because this function margin is negative, you end up with a penalty bigger than 1. So second case. And there's an intermediate case. Example is correctly classified, but it falls within the margin. And what will happen here? We can just look into the value of this max function, right? So if your example is correctly classified, that simply means your function margin is not negative. But it is within the margin, right? It breaks into the margin, that means the function margin is less than 1. And then 1 minus some value less than 1 is still positive. That means you still incur some penalty. The penalty is still here. It's 1 minus the function margin. So now you can say, even if you do the right thing, right? You correctly predict the example. But if the example, your hyperplane is too close to the example, you still have to bear out some punishment, right? So we define this penalty as hinge loss. This is a very common used term. It's kind of common sense in machine learning, right? And whenever you talk about like hinge loss, it's just to talk about this function. It's max of 0 and 1 minus the function margin. We call this penalty term as hinge loss. And to give a even clearer look at this hinge loss, we just draw is graph. So here, the right line indicates the 0, 1 loss. 0, 1 loss. So what is 0, 1 loss? Simply, it's two-value step function. If you misclassify example, your loss is simply 1. If you correct classify example, your loss is 0. That means you have no penalty. This is kind of ideal loss function to evaluate the performance, right? But here is the hinge loss. Oh, by the way, the x-axis is the value of the function margin. That is production between your ground truth label and your classification function value. So now, we can see first, this is the wrong loss. So first, if make a wrong prediction, that means your function margin is less than 0, right? It's on the left-hand side. Then you have a large penalty, right? Quite a large penalty. An interesting thing is that when the absolute value of your function margin is getting larger, that means your function margin goes along this way, right? And then your penalty, your hinge loss becomes larger and larger. So it implies that when you make wrong predictions, it will penalize more when you make when your mistake is more and more wrong. It will give penalty based on the severity of the mistake you make. So obviously, if your prediction is wrong, right, then the larger the absolute value of your function margin, the more wrong you make. Then you incur a larger penalty. And if your function margin is less than 1, then we're satisfied. You have 0 penalty. That means your hinge loss reaches the minimum value. As you just mentioned, right? As long as it's bigger than 1, no matter how you more correctly give the prediction, we just give you the reward 0. We don't increase the reward. This is kind of like opposite direction to do this, right? You will make your severity of the mistake. If your mistake is more and more severe, you need to bear more punishment. Right? But if you're doing the right things, you're doing no matter how right you're doing, like after some degree, that's it, right? You don't do any change. Right? You don't give you more rewards. But there's some intermediate region. Right? So even if you make correct prediction, say the function margin is between 0 to 1, but the loss is still non-zero. The hinge loss is still non-zero. Why? Because you are too close to the classification boundary. You break into the margin, although you still make the correct predictions. And also this loss or this penalty will be increased when you get farther and farther away from the classification boundary. If you finally end up with like staying outside the margin, then your penalty is simply 0, and vice versa. Any questions so far? Okay, this is about the meaning of the hinge loss and how is it proposed. So now I want to generalize this idea. We know the cost function of our support vector machine model consists of 2 components. The first component is to maximize margin. The second component is to put penalties over your prediction on training examples. So if we look at the bigger picture, right? So if you are responsible to build some classifiers, right? How do you design your objective function, or how do you design your optimization problem? So in general, we have 2 strategies. So the first strategy is called risk minimization. So what is risk minimization? We simply define a loss function over each training example. So if you correctly predict your training example, well, you have no penalties, or even you can enjoy some reward. If you make a wrong prediction, we need to punish you. We just define such kind of loss over the training examples. And then our learning objective is just the summation of the loss over the entire training examples. And the learning procedure is to find a classifier or hypothesis that has the lowest loss of training data. This is the first strategy. Question is this strategy okay? What's the potential problem of this strategy? So remember, we have some example under this, some example machine learning model under this risk minimization principle. What is that model? You all have implemented this model. What is this model? Yeah, exactly, right? So least square method for linear regression is a typical example of risk minimization. Why? Because the objective function is the summation of the square errors over each training example, right? So the square error is the loss. So here I want to ask, like, what's the problem with this principle? Any guess?
Examples that defy the hypothesis, or that, destroy the margin.
But that doesn't matter. But I think you're kind of show some flavor I want to express. Yeah.
Well, just the usual with the training data will be different than other data.
Here you are referring to some very important point, but try to be more explicit. Yeah, you are talking about the difference between what?
Overfitting?
Yes, exactly. You have the same. Yeah, overfitting, right? So if we just want to minimize the training error, right? I can choose like very complicated models. I can build up like 1,000 layer neural nets and 10 million parameters. I'm sure they can give you zero training error for whatever training data you have. But what is the risk? You overfit the training data too well, right? You fit the training data too well, overfit data. If there are some noise in data, you end up with very bad generalization performance. So that could be a problem. From the computational learning theory, right? We have known that if we have two models both can fit data very well, we like to prefer the model which is less complex, which is less expressive. That's why we introduce DC dimension, we introduce a large margin principle. So there comes the second principle. It's called regularized risk minimization. So how does this word regularize mean? It means in addition to the training loss, we introduced a regularization function that penalizes over complex models. So basically, we want to find out a trade-off between the fitting of the training data and the complexity of the model. And then the learning is to find out a hypothesis or classifier, whatever, has the lowest value that combines the regularizer and the loss from training data. So this is called regularized risk minimization. So what is the example of learning algorithm that uses regularized risk minimization? An idea?
Decision trees we would not go down too far. We would find a level to prune at.
Yeah, that's a very good example. Right? If I like intentionally prune trees or just restrict the size of trees, we're fulfilling this regularized risk minimization, right? Any other example? SVM, right? The classifier we just discussed, right? So remember the cost function consists of two components, right? So the first term tries to maximize the margin, right? What does maximizing margin mean, right? It's to analyze too complicated models. Right? If your model is too complicated, that means you use too expressive hypothesis space, you end up with big basic dimension, right? You end up with a larger generation error bound. So this is a regularization term. And the second term is the hinge loss. You know that hinge loss penalize your incorrect classifications and also degrade your misclassified examples. And of course, when you design your own learning algorithms, right, you can modify this objective function. You can say you can replace hinge loss by other kind of loss functions according to your own flavor, or depends on applications, whatever. For example, like in many applications, we know that if you misclassify positive examples, and it will have a different cost for you if you misclassify negative example. So, for example, you want to do a diagnosis. If somebody is normal, you predict he has an ill, was fine. You can do some more accurate tests on that, right? But if some people, like, they have some illness and they say, okay, you're perfectly fine, then the consequence is severe. And you can modify the hinge loss accordingly. So actually, there are numerous variants of small vacuum machines. They're just trying to modify this hinge loss in this place, in other place, and whatever. And finally, we have a regularization term, right, which penalizes the complexity of models. We have a loss term which penalizes the training error, and we want the trade-off, and this is hyperparameter. Okay, that's all about the objective function support vacuum machines, and we can stop early today, and hope everybody enjoys the wonderful spring break. And after you come back, we'll continue with SVM.